Hi everyone, and welcome to RUBIN'S MindLab, where we break down the latest research into what it really means. Ever wondered if the tests you take, especially online or in big studies, are actually measuring what they think they are? Or if you retake a test after the people who made it learn more, would your score change and would it be more accurate? Well, this new study dived deep into that very question. Imagine you are building a special tool, but you are not really sure about the measurements of all its parts. That is kind of what psychologists and educators face when they create computerized adaptive tests, or CATs for short. These are tests that change the questions they ask you based on how well you are doing. They're super efficient, but they rely on having really good information about each question, like how hard it is and how well it separates different ability levels. The problem is, sometimes they have to use information that is not quite right, maybe from a small test run or data from a different group of people, or even just the best guess. This paper asks a really important question. Can we fix the scores people get on these tests after they've already taken them, if we get better information about the questions later on? So here is the big idea the researchers had. When a CAT's questions are not perfectly calibrated, meaning the information about them is off, it causes two main problems. The first is called item selection error. This is when the test, because it thinks a question is easier or harder than it really is, asks you the wrong questions. It's like a salesperson showing you a suit that doesn't fit because they misread your size. And the second problem is scoring error. This is when, even if you get the same questions, the calculation of your final score is a bit off because the underlying information about those questions is faulty. Think of it like using a ruler that is a little warped to measure something. Now, here's the crucial part. The researchers realized that while you can't undo the wrong questions you were asked, you can potentially fix the scoring error. They call this rescoring. If you get better information about the questions later, you can go back and recalculate everyone's scores using that new, better information. And guess what? It doesn't require anyone to retake the test. To figure out how big of a deal this is, they did two main things. First, they ran a big computer simulation. They created a fake item bank, messed with the question parameters in different ways, and then simulated how different people would take these tests. They compared the scores people got when using the bad information versus what they would have gotten if they used the good information. This is a really smart way to control everything and isolate the impact of the miscalibration. Then, importantly, they tested this idea in the real world. They looked at data from a study called the Levante project, which involved thousands of kids aged 5 to 12. These kids took different cognitive tests, and the researchers found that the initial information about the test questions was indeed miscalibrated. They then applied their rescoring method to this real data and compared the old scores to the new rescored values. In the simulation study, they tested 3 different ways the question information could be wrong. They looked at random guessing errors, systematic shifts where the difficulty was consistently off, and cross-population misalignment where the order of difficulty changed between different groups of people. And here is what blew them away. Across all these different types of errors, they found that the scoring error accounted for a huge chunk of the total problem. It was between 86% and 96% of the accuracy loss that was due to the bad information about the questions. This means that most of the harm done by using wrong information could actually be fixed just by rescoring with better information. In the simulation part, when they looked specifically at misalignment between different groups of people, which is super common when you use the same test in different countries or cultures, they saw that the error went way up as the alignment went down. But again, when they rescored the tests, the new scores were much closer to the true scores if the test had been perfectly calibrated from the start. This figure here is pretty neat. The red line shows the error when using the bad information. As you move left, the alignment gets worse, and the error shoots up, but the gold line, that is the error after rescoring. See how it stays low and close to the perfect benchmark blue line. That orange shaded area between the red and gold lines, that is the scoring error, the part that rescoring fixed. It is way bigger than that gold shaded area, which is the selection error, the stuff rescoring can't fix. This visually shows just how much of the problem is recoverable. They also looked at how the errors happened. Sometimes the scores were just generally wrong in a consistent direction, that is bias. And sometimes they were just all over the place, that is variance. For some types of errors, the original scores had a lot of bias, meaning they were consistently off. But after rescoring, they found that this bias was almost completely eliminated. It went from sometimes making up 90% of the error down to less than 0.5%. That is a massive improvement in accuracy. This table really highlights how well rescoring works to get rid of systematic errors or bias. Look at the Cato columns, which are the original scores. The bias can be quite high, especially with structured shifts. But then look at CAT-R, the rescored scores. The bias is tiny, practically zero, no matter what kind of error they simulated. This means rescoring really helps to ensure the scores are fair and not systematically skewed. What is also interesting is that the benefit of rescoring is even bigger for shorter tests. This is super relevant for tests given to young children who might not have the attention span for long tests. The simulation showed that the gap between the old and the rescored tests was largest for shorter test lengths. This figure shows how the accuracy difference between the old scores, red, and the rescored ones. Gold changes as more questions are asked. You can see that for shorter tests, the gold line is much closer to the perfect blue line than the red line. This means that for those who only take a few questions, the improvement from rescoring is really significant. Now, for the real-world study with kids, they looked at data from thousands of children aged 5 to 12 who took different cognitive tests like math, matrix reasoning, and others. They found that the original question information was indeed pretty messy, with some questions having wildly inaccurate difficulty values. The researchers then compared the kids' scores calculated with the old messy information to scores calculated with the new, cleaned-up information. And what they found mirrored the simulation. The scores shifted, and in some cases, kids completely changed their rank order compared to their peers. This table summarizes the changes. The R column is a measure of how much the kids' relative positions changed. A lower number means more kids change places. For example, in matrix reasoning, with pretty bad initial alignment, that is the value of 0.34, the correlation is 0.89, meaning there was substantial reordering. The column shows the average shift in scores. For mental rotation, the average shift was a huge minus 1.82 logits, meaning the original scores were way too high on average. This shows that rescoring didn't just nudge scores, it made significant adjustments. And here is a really important point about fairness. They found that the children who were most affected by these score shifts were often the ones with lower abilities and the younger children. This makes sense, as we saw in the simulation that shorter tests and tests with more imprecise question information hurt lower ability and younger kids more. This means that using miscalibrated tests could unfairly disadvantage these groups. Rescoring helps to fix this, making the tests more equitable. But were the new scores actually better, not just different? They checked this by looking at how well the scores related to age, since kids should get smarter as they get older. For matrix reasoning, which had the worst initial alignment, the correlation between scores and age got significantly stronger after rescoring. This means the rescored scores did a better job of reflecting a child's actual developmental progress. They also checked if scores on different but related tests correlated better after rescoring. And for the most part, they did, showing that the new scores were more consistent and reliable measures of related cognitive skills. This table shows the improvement in how well different tests correlated with each other after rescoring. See the R column. For most pairs of tests, this number is positive, meaning the correlation got stronger. For example, math and matrix reasoning scores correlated much better after rescoring. This suggests the new scores are more accurate and consistent across different measures of cognition. So, what is the big takeaway from all this? This research strongly suggests that rescoring is a powerful tool. When tests are built using imperfect information, most of the resulting score errors, between 86% and 96% of them, can be fixed post-testing by simply using better information about the test questions. This is a post-hoc fix, meaning it can be done after the fact without making anyone retake the test. The researchers emphasized that while rescoring can't fix the selection error, the fact that you might have been asked the wrong questions, it is incredibly effective at fixing the scoring error. This means that even if the test assembly wasn't perfect, the final score calculation can be significantly improved. This is crucial for programs that deploy tests quickly, perhaps across different countries, or using AI-generated question parameters, where perfect calibration might not be available at the start. They suggest a strategy: deploy a test quickly with the best available, even imperfect, information. Then, as more data comes in, recalibrate the questions and rescore the existing data. This allows for rapid deployment and iterative improvement of test scores. This is also super relevant for new technologies. AI is being used to help generate question difficulty estimates. While these can be a great starting point, they might not be perfect. This research shows that even if the initial AI-generated parameters are a bit off, rescoring can still salvage the accuracy of the scores later on. It acts as a safety net, and that part about equity is incredibly important. The study highlights that using miscalibrated tests can disproportionately disproportionately harm lower ability and younger children. This means that rescoring isn't just about making scores more accurate. It is also about making tests fairer for everyone, especially those who might be most vulnerable to measurement error. Now, it is not a magic bullet. The researchers are upfront about the limitations. Rescoring can't fix the problem of being asked the wrong questions initially. Also, getting the final rescored scores takes time because you need to collect enough data to recalibrate the items first. And while they could show that the rescored scores were better based on external measures like age and other test correlations, they didn't have a true score for each child to directly compare against. But overall, the message is powerful. Rescoring is a vital step for any CAD system that might be using early-stage transported or AI-generated item parameters. It makes tests more accurate, more reliable, and ultimately more equitable without asking anyone to do more work. For any large-scale testing program, especially those expanding across different groups or languages, recalibrating and rescoring should become standard practice. This research really underscores how important it is to not just build a test, but to continually refine and improve the information we have about its components. It shows that even with imperfect beginnings, we can often salvage and significantly improve the accuracy and fairness of our measurements. It gives us a practical strategy to make assessments better over time. What do you all think? Have you ever taken a test multiple times and noticed your score changed when you got the results back? Let us know in the comments below. If you found this breakdown helpful, please give this video a thumbs up. Subscribe to RUBIN'S MindLab for more science explained simply. And hit that notification bell so you don't miss our next exploration into the human mind. Thanks for watching, and we'll see you next time.